Hello everyone, my name is Pauline Colinet, and in this talk we will focus on how to improve the efficiency of electrostatic embedding with the aid of the fast multipole method. So to give a bit of context, electrostatic embedding are involved in QMMM and ECM methods, ECM standing for Embedded Cluster Models. It's kind of a QMMM for solid state if you want. And we will mostly focus on that in the following slides. So the idea is the same. You put most of the computational effort on a well-localized area of interest, your quantum cluster, and the effect of the rest of the solid is approximated by embedding your quantum cluster into an array of point charges. If we decompose the total energy of the system through an additive scheme, we can say that it is equal to the energy of the quantum part, the energy of the array of point charges, we don't care about actually, and the coupling term between the QM and MM part. In the scheme of the electrostatic embedding, this coupling term is the electrostatic potential generated by the point charges and felt by your quantum cluster, and this is evaluated through these one electron integrals here, with Qm the point charge in the environment and Nr the density of your quantum cluster. So we have mainly two terms, this Qm part and coupling term, and if we want to increase the size of our systems, this can actually become computationally demanding. And in this talk, we will mainly focus on the coupling term, and we want it to be as small as possible. So just to illustrate the cost of this coupling term, here is a quantum system made of 136 atoms. And in white, the right rectangle represents the total time spent for a single point calculation. Depending on the number of point charges in your environment, you might spend more or less time for this single point calculation. And in gray is represented the percentage of time spent in the evaluation of the one electron integrals. So depending on your properties, you might need more or less point charges, but for an average case of 75,000 point charges, you are already using almost 30% of your computational time just to evaluate this one electron integral. So we want to reduce that. In order to do so, we will use the fast multipole method, which has been developed by Gringard and Rocklin in the late 80s. And the principle is the following. You put your system into a box, and then you divide this box 1 time, 2 times, 3 times, up to a certain level, which is a parameter of your method. And at this deepest level, for every box B, you can evaluate the potential and say that it is there is a term due to the near field potential, due to the nearest neighbors boxes in purple, and a term due to the far field potential, which is due to the rest of the boxes. You can further decompose into the green local far field and the gray remote far field. The idea then is quite simple. In the near field, we will evaluate the one electron integrals, but in the far field, we will approximate those interactions. This is what will save computational time. So how do we do that? How do we approximate these one electron integrals? The idea is to expand the 1/r term here in this expression into what we call a multipole expansion, which gives a name to the methods. So we don't really care about the mathematical details here, but what I want to highlight is that this series converges, but you have to go up to infinite, and this is in practice not possible, so we have to truncate the summations up to a certain value, which is also a parameter of the FMM. This Lmax value, which is actually the maximum angular momentum of some underlying spherical harmonics in the expression, has to be set in the input of your calculation. So the higher the value, the more accurate you will be. This 1/r also expansion through the multipole expansion enables you, after some mathematical rearrangement, to write your summation over all the one electron integrals into a nice and very efficient vector matrix vector multiplication, which makes the FMM very efficient. Another ingredient in this algorithm is a recursivity. So we can see it on this scheme here. At the last level here, level 3, the far field felt by box B is due to the local far field in green and the remote far field in gray, which is actually the local far field of the parent box of B. So in the end, we can only calculate the interaction with the local far field box at every level and translate this information to the children box. this recursivity is actually depending on the number of levels and makes the algorithm extremely efficient. So the question now is how to choose the parameters values, how to choose the Lmax and the number of levels. To answer that, I took here an example system I worked on in the past to study some spectroscopic properties of defects in this solid material. And in order to do that, I used an ECM approach. So I reused my setup and I applied the FMM in order to save some computational time. So first of all, I looked at the accuracy, that is the error I would get with respect to the reference calculation, that is without using the FMM. This error is reported here. It's a log of the error. So as we go down, we increase the accuracy. On the x-axis, I increase the truncation parameter of my multipole expansion in the far field. And as we can see, as we do that, the error decreases, which is expected. After a value of Lmax of 15, we actually have reached a millihartree accuracy, which is lower than the 1 kcal per mole chemical accuracy. The TD value is 3 depths, the number of levels in your system, and this does not impact much the accuracy. Okay, so the algorithm is accurate. We can now check how fast it is. So here I report the time spent in the calculation of the 1 electron integrals without using the FMM, and with using the FMM with 3 levels here on the right. The different rectangles correspond to different truncation parameters of 5, 10, 15, 20, and 25. And we can see that as we increase this parameter, we increase the time spent in the evaluation of the 1 electron integrals. I have decomposed the time spent in the evaluation of the 1 electron integrals between the far field and the near field in red. So the near field does not depend, obviously, on the truncation parameter. If I add 1 more level, I will decrease dramatically the time spent in the evaluation of the near field in red here, which is expected because I have decreased the size of my boxes. And again, as I increase the truncation parameter, I increase the time spent in the evaluation of the far field. I do it 1 more time, I barely see the time spent in the near field, and here I'm 28 times faster than the reference calculation. And if I do it 1 more time, I have a 3 depths of 6, then I start increasing the total time spent in the evaluation of the 1 electron integrals because I start paying the cost of translating the information between levels. So we need to find the right balance between decreasing the evaluation of the near field part and increasing the evaluation of the far field potential. So it's not straightforward to find a good number of levels. So we did many tests on different systems, on different solid state systems, but also on different molecular systems. And we found out that the best input box dimension is 9 bars, and this will set up the right number of levels for your system. So this is a default parameter now in the ORCA FMM. And regarding the truncation parameter, the value of a value of 20 for Lmax will actually ensure that you are more accurate than the chemical accuracy of 1 kcal per mole. So you can call it in ORCA through the keyword line, FMM QMMM. This does not replace the QMMM keyword, but you should check the manual to get all the information and details. And if you want to tune some parameters, like for instance, the maximum angular momentum, if you want to reduce it, you can inside the method block, define a new value for your maximum angular momentum here. There are other parameters I haven't talked about during this talk, but once again, you can find everything in the manual. So just as a matter of illustration, there was the effect of adding more point charges into your environment onto the percentage of time spent in the evaluation of the 1 electron integrals without the FMM. And now if you use the FMM, you don't see anymore the impact of increasing the size of your environment. This doesn't cost you more than 4% of your total calculation time, which is exactly what we wanted. So you should, whenever you use an electrostatic embedding, turn on the FMM in order to save some computational time. So to conclude, I couldn't really talk about it, but these ECM approaches are really complementary to periodic boundary condition calculation in material research. And if you want to set up your own input, you should check the ORCA crystal prep tool. This computational solid-state chemistry with ECM are actually now, as you could see, accelerated thanks to the implementation of the FMM in ORCA. And you can play on the accuracy of your calculation by tuning the truncation parameter or the efficiency by adding more or less levels in your hierarchy. So this implementation has been actually done in a general way. So you can also use it also for QMMM calculations. And of course, this is available within ORCA 6. So I thank you all for your kind attention, the whole ORCA team, of course, especially Benjamin Helmisch-Paris and Frank Nese, and the fundings.